Section 4.8, Video 2, Probability Trees and Binomial Experiment. We will continue with the objectives of using probability trees to calculate probability of conjunctions, probability of disjunctions, and also conditional probabilities. Let's work on example 3. Create a probability tree for the following experiment. A bag of marbles contains 6 yellow marbles and 4 green marbles. Create a probability tree for the experiment of choosing 3 marbles without replacement. Then we'll find the 2 probabilities requested. When reaching into the bag of marbles from our start, we have 2 possible results. Either a yellow marble could come out or a green marble could come out, and that represents the 2 branches, one branch being yellow and one branch being green. Since there are 6 yellow and 4 green marbles, there are a total of 10 marbles. That would be our denominator. The 6 yellow marbles means our probability of choosing yellow is 6/10, and 6/10 goes on the yellow branch, and the probability of green is 4/10, and that goes on the green branch. I tend to not reduce at this point. I tend to wait until the end for my final answer. I like to see that the 6/10 and 4/10 adds up to 1, and then I just decide to wait until the end to reduce. The next time, for the second time choosing a marble, there could still be a yellow option or a green option, no matter what came out the first time. So I'm going to write yellow branch and green branch off of each of the first branches for a second set of branches. This time, though, because the marble was not replaced, we have to think through each scenario. So in the first case, following the yellow branch, a yellow marble was taken out and it was left out of the bag. So now our denominator is going to be down to 9 marbles in the bag. And that actually would be the case for all of the branches in this second scenario. If a yellow was taken out first and there were 6 yellows to start, the probability of yellow is now 5/9, and all 4 green marbles still remain. Notice that the probability of that branch of yellow and branches of yellow and green total 9/9. In the second scenario here, if a green was taken out first and left out of the bag, there are still 9 marbles in the bag. And now 6 of the yellows remain, but only 3 of the greens remain because there were 4 green and 1 was taken out and left out. Third time reaching into the bag, we still have those same 2 options of yellow and green. So I'm going to draw a yellow branch and a green branch off of each of the 4 branches that were already there, giving a total of 8 branches. In the top scenario, a yellow came first and a yellow came second. So now there are only 8 marbles in the bag. And if we were at 6 yellow and we took 2 out, we're down to 4 yellow and all 4 green remain. Notice the total of 8 8s there. In the second scenario, a yellow came first and a green came second. So 1 yellow and 1 green were taken out of the bag, meaning we're down to 8 marbles in the bag. And we're down to 5 yellow marbles and 3 green. In the third scenario, that a green was taken first and a yellow was taken second, we're again down to 8 marbles in the bag. And because one yellow was taken out, we're down to 5 yellow. And because 1 green was taken out, we're down to 3 green. That totals 8 8s. In the last scenario at the bottom, a green was taken out of the bag and a second green was taken out of the bag. And so our total is down to 8 marbles in the bag. But with 4 green to start with and 2 green coming out of the bag, we're down to 2 green marbles, but all 6 yellows remain. And that set of yellow and green branches also totals 8 8s. Let's go ahead and put the final amount at the end of the branch for the complete total of that branch. So 6/10 times 5/9 times 4 8s would give 120 out of 720ths. The next branch would also be 120 out of 720ths. The third branch would also be 120 out of 720ths. The fourth branch, 6/10 times 4/9 times 3/8, would give 72 720ths. The fifth branch would be 120 720ths, 72 720ths, 72 720ths, and then the final branch at the bottom would be 4/10 times 3/9 times 2/8, or 24 720ths. Let's take a look at Part A. Part A says find the probability of yellow, then green, then green. When they're written with that order and commas between them, it is an order that is specified. So I'm going to follow the yellow branch first, the green branch second, the green branch third, and I get a total of 72 out of 720ths, and now I'm going to reduce that to be 1/10. Part B is a little bit more difficult. Find the probability that there's at least one yellow marble given a green was first. So we could use the probability of the intersection over the probability of the given to calculate the conditional probability. But because green was listed first, we could also use that shortcut of moving the starting position. So I'm going to move the starting position to what we know for sure happened, and that green was first. So I'm going to ignore the rest of the probability tree, and I'm going to focus on the part of the probability tree that's after green being first. Okay, and so following that, we see that if we want at least one yellow, we need to follow the yellow branch, which is 6/9 times 5/8. We would also follow the yellow-green branch, which is 6/9 times 3/8. And there's another branch that meets this description of at least one yellow, and that would be green and then yellow. And that's a probability of 3/9 times 6/8. So our first product would end up being 30 out of 72, our second 18 out of 72, and our final 18 out of 72, giving a total of 66 70-seconds, and then reducing, we get 11/12. Now again, you could reduce sooner if you prefer. I tend to reduce in that last step. Let's take a look at example 4. Consider a competition where two teams are competing, and the team that wins the majority of games wins that series. We're going to be looking at a best-of-3 competition. In our best-of-3 competition, the home team tends to have the field advantage, and the probability of them winning could be higher. For the purposes of this textbook, we're going to assume that the location of the games is going to change each game. So in our problem given, the Bandits and the Thunder are in a best-of-3 baseball competition. When the Bandits play on their home field, the probability of winning is 0.62. But when the Thunder play on their home field, the probability of winning is 0.55. The Bandits are going to start out with the best team record, and so they're going to have the home field advantage first. And then the location of the games is going to alternate. The Bandits will have it first, and then second game they'll travel and play on the Thunder field. So let's go ahead and begin writing our best-of-3 competition. I'm going to start, and with the first game there are two options, so we're going to have two branches. One is that the Bandits win, and the other is that the Thunder win. It's important because the probability of the changes with who wins based on the location of the game. So above this set of branches, I'm going to write that the Bandits are the home field. So the probability of the Bandits winning on their home field is 0.62. To complete that branch, this is the probability of the Thunder winning, while at the Bandits' home, not at the Thunder's home, while at the Bandits' home. So remember how we said a set of branches has to total 1? So we can calculate this as 1 minus 0.62 from what we had, which is 0.38. Now we can move on. So game 1 is done. We can move on to game 2, and we still have 2 choices. The Bandits could win or the Thunder could win. And so I'm going to go ahead and draw those 2 branches. And this time the game moves to the Thunder being the home field. Now remember that it says the Thunder playing on their home field, their probability of winning is 0.55. So make sure you look at the Thunder branch of winning is 0.55. Using that same idea that the set of branches has to total 1, 1 minus 0.55 would be 0.45 to make sure that set of branches totals 1. And then we would repeat those probabilities. The Bandits would be 0.45 and the Thunder would be 0.55, looking at following the Thunder winning the first competition and the set of branches for Bandit and Thunder. If a third game is needed, we go back to the Bandits being the home field. But keep in mind, we don't always need a third game. Consider this top scenario. The Bandits win the first game and the Bandits win the second game. The competition is done. The Bandits have won 2 out of the 3 games. Here, the Bandits win, and they're done in 2 games. The next scenario is the Bandits won the first game and the Thunder won the second game, so they're tied 1 game each. There needs to be a third game, and either the Bandits could win or the Thunder could win. But because we're back at the Bandits' home field, the Bandits playing on their home field, the probability of winning is 0.62. So 0.62 for the Bandits, and 1 minus 0.62 is 0.38 for the Thunder. In that next scenario, Thunder wins the first game, Bandits win the second game. It does go on to a third game. Remember, the Bandits are still considered home field, so still 0.62 probability for Bandits and 0.38 probability for the Thunder. In that bottom scenario of 0.38, of the Thunder winning the first game and the Thunder winning the second game, here the Thunder have already won, and there's no game 3 needed. Now let's complete our tree by putting the probabilities at the end of each branch. So remember the probability of intersection, we're going to multiply 0.62 for Bandits win first and 0.45 for Bandits win second, and I get 0.279 or 279 thousandths. Let's take a look at the next one. Bandits, Thunder, Bandits. We get 0.21142, and that would be 21,142 hundred thousandths. The next one down, I'll go ahead and 12,958 hundred thousandths, 10,602 hundred thousandths, 6,498 hundred thousandths, and that bottommost set of branches, 0.38 times 0.55, we end up with 0.209 or 209 thousandths. Notice that if you added up all of these ending branch probabilities, you should get 1. Let's take a look at part A. The Thunder win the series. So any branch where the Thunder win 2 out of the 3 games would be part of what we want to total. So if we look, we want Bandits, Thunder, Thunder. We're going to take that probability, 0.12958, 12,958 hundred thousandths. We could also have Thunder win first, Bandits win second, Thunder win third, or Thunder win in 2 games. And so adding up those probabilities, remember if we have more than one branch that meets the description, we add them together to increase the probability. And I get 0.40356, or 40,356 hundred thousandths. Part B looks at find the probability that the Bandits win the series if we know the Thunder won the first game. Now this is another one of those that we can move that starting point. If the Thunder win the first game, I'll use blue in this case. If the Thunder win the first game, that I can move my starting point to the end of Thunder's first branch. And then I'm going to follow the branches where the Bandits win the series. That would be that the Bandits have to win the next 2 games. And so we would multiply those 2 branches together, 0.45 times 0.62. And we would end up with a total of 0.279, or 279 thousandths. And that ends example 4.